Hopefully this will work. Now I need this. So right now you should see the first slide and hear me. At least microphone is blinking green, which is a good sign. And well, WebAssign should work. Although some students informed me and everybody else yesterday about some issues with WebAssign. I'm not sure that's on a WebAssign or connection or something else. On my side, it actually works pretty good. And right now we are taking lecture number 19. And if I open it, you can see that question number 2 is a copy of the question on the screen. So you don't have to look at the screen. You can go to WebAssign and start answering. What I would like to say is a couple of things. So first of all, I thought that my instructions were clear enough. If you're a student, after the exam, take your pictures, email to a grader, teaching fellow. If you're a teaching fellow, after the exam, receive the emails, copy, grade. However, to my knowledge, about 2,000 students still have no human grade on Blackboard, but they have grade on WebAssign. So this is not a very representative distribution because it's a mixture of grades, so it doesn't tell much. Just an example of a distribution, and you can see some grades are high, some grades are low, and for students who have both grades, WebAssign grade and a human grade, again, most of the time the WebAssign grade is lower than the grade given by a human. And I also can see this time more students have a grade in a lower percentile. Well, it is not a new fact. Since the beginning of massive open online courses, it's been measured again and again that the completion rate for online courses is much lower than the completion rate for on-site courses. So it's not just about, I don't know, content or pandemic. This is the format. For some students, this format works fine, and for some students, this format brings extra challenges. Even before the pandemic. So this is from 2018 and 2019. And this example with an email that says classes will not be affected, but they are, is a good example of a law. There is a law in the universe that says an ability to manage others begins from an ability to measure, to manage and measure and manage themselves. Currently, as we can see, on many levels of management, not just university, all levels, people breaking this law. Well, recording is happening. Now let's see if I can see something. So someone is asking, if we didn't receive a human grade, should we email the TF? Well, today in the morning, about an hour ago, I sent an email to the whole class. It had two parts. Part number one, the link to this Zoom meeting. And part number two, about the grades. That part said explicitly, if you check your grades on Blackboard and you see a missing grade, maybe it's a lab grade, homework grade, or exam grade, first, you should contact your grader, teaching fellow. So that's what you're supposed to do. WebAssign grade, it depends. Homework grade, yes, contact me. All right. Well, moving on to physics. Again, there is a homework that actually was opened yesterday, and again, this homework has a standard deadline, which is the day before the exam, in the several recommended deadlines, plus or minus. And again, as I checked yesterday, before the exam number 2, some students didn't finish the full homework, including the last part on torque, and those students may have had an extra difficulty with problems on torque. Everything is related. And this is what we are talking about now. Good thing we saw experiments before the exam. These are the systems which all exhibit a similar behavior. All those systems have in common a stable equilibrium state, the location when the system is at that location and left at that location at rest, it will remain forever at rest at that location. But if we deflect, move the system away from equilibrium by a little bit and let it go, in that case, there is an action, an effort, a force, a torque that always points back toward equilibrium, that always wants to restore the equilibrium, and that makes the system move toward the equilibrium, but it passes it. And as an experiment, I'm gonna try to do this. And now, do this. Too much. Too much, too much. Well, issues. Missed exam, missed power, missed Echo 360. Those issues always require extra time to be investigated and fixed. That extra time, of course, doesn't go from anything but from talking about physics. So right here, right now, we have that system, an example of it. It's in equilibrium and it can stay in equilibrium forever. if I give it a hit, give it a push, like in exam, one single push, it starts moving, but it doesn't fly away because there is always a force that wants to bring it back to equilibrium, but it doesn't stop here. Nothing catches it. So it keeps traveling by inertia through equilibrium on another side, and then the force wants to move it back again and again and again and again. And we can change some parameters. I cannot change the springs here. Well, I can make them a little bit shorter. So it's going to make them a little bit stiffer. How does it affect the motion? You can see clearly it moves back and forth faster. So to describe this motion, we use a physical quantity called one period, the time for one whole motion, one period. So we decreased the period. But if now I make it heavier, if I add some mass, what do you observe? What do we observe? It takes more time to make one whole revolution. And that means now the period is larger than before. So we can manipulate with these variables spring, and we know now to describe the property of a spring we could use a spring constant or mass. Moving back to sharing the screen, and the recording is happening. So, and my backup is back. Well, chat, and I need to move ahead. Question to you for the WebAssign review. You can see here a straight line. It represents something. What does it represent? Well, you could read the axis. The horizontal represents the x coordinate of that cart, and the vertical represents the x component of a force acting on that cart. So, if we want to describe this graph, what equation would we use? And I'm going to check what is happening again on a WebAssign. On a WebAssign. That's the question number 3. So we're losing small portion of a screen, but I think that's okay. So we've got 50 students. For the question number 2, the majority said the exam was somewhat harder than I expected. Some said about as expected. Some said somewhat easier. And some said much harder. This is again just a clear proof that we cannot rely on our feelings. Our feelings lie. Facts don't. And question number 3, this one, the most popular answer is number 2. Which is, of course, is correct. Because here, for every positive x, we've got a negative value for the x component of a force, and for every negative x, we've got a positive value for the x component of the force. So to represent this relationship, we have to use a minus. Well, and we need to remember that in general, we choose the origin, and we could choose it anywhere we like, but this expression is based on the assumption that delta x equals x, or x minus 0. This represents the fact that the origin was set at the equilibrium position. For all our problems, that is almost all problems, that is always a case, but in a lab, that may not be a case. The lab will be on Monday and Tuesday. Next question. Well, basically, it's a problem. We have attached a 100-gram weight to a vertical spring. This spring stretches by 10 centimeters. What do you think is the spring constant or force constant of that particular spring? So this is a problem. It requires to be solved. And the solving process, of course, begins from what? From a picture. That's what everybody should be doing right now. I'm going to give you some time and draw my picture as well. This is a review. We did it before. We had a spring. I placed it on a table, and at first, nothing was attached to it. Then, we added a weight to it, and the weight stretched the spring by a certain amount. Right now, it's not moving. Velocity remains 0. That means this is the equilibrium position. That means if I wanted to describe the motion of this weight on this spring using a coordinate axis, this is where I would set my origin. And even if it's not a part of this problem, but what we could do, we could stretch the spring a little bit longer. So this is not the equilibrium anymore. And if we release this object from rest, the restoring force would make it move toward the equilibrium. Now the initial velocity would not be 0, but the object would travel through equilibrium, stop a little bit above it, then would be traveling back to equilibrium, and it would be moving up and down, up and down, up and down, up and down, theoretically forever if we neglect friction. So that's for future. For now, what we know is the spring was stretched by this amount. This is the elongation, the stretch, which is 10 centimeters, which is 0.1 of a meter. Why did it happen? Well, this is a picture, not a diagram yet. What's missing? You see, we are moving toward the last exam, but we still talk about things we learned before the exam number 1. We have to add force of gravity. We have to add that elastic force, Hooke's force. And because it's not just velocity equals 0. Velocity here is also constant. That means acceleration is 0. That means net force equals 0. That means Fx minus mg equals 0. Now all we have to do is just combine these two equations. This is the Hooke's law. This is the Newton's law. They've been rivals. Hooke told that Newton kind of stole his ideas. And Newton said, no, I came up with those ideas way before you did. So they didn't like each other. But their laws perfectly work together, right? So, of course, it's easier to use magnitudes. In our case, the magnitude of this force equals mg, and the magnitude of displacement equals elongation. What is m equal to? Oh, you couldn't see it clearly. Well, I said it, it's 100 grams. So 0.1 of a kilogram, g is about 10. This is 0.1, 10. 10 what? Well, we got a Newton in the numerator and a meter in the denominator of this fraction. So that's the unit. Well, now the description. Well, what's good about this motion is kind of simple. Yeah? It repeats itself. Let's say this ball at t equals 0 is released from rest. The initial velocity is 0. What's going to happen? Well, we can actually draw a motion diagram. Remember lecture number 5, or maybe even 4. The motion diagram shows the location of this object at, well, different instances, like every second. So what's going to happen? Well, in a second, it's going to move closer to equilibrium, but then it travels faster, but then it slows down and it stops. But not forever. It reverses the direction and then it travels back, passing the same locations. And now this one motion represents one period. Now we've got an extra sound that is coming from, I don't know where. And the controls do not work, so we have to deal with that. All right, so this is what one period is. But we can measure how many oscillations it makes in a certain amount of time. In that case, the period would have been this ratio, the amount of time over the number of oscillations. But the number of oscillations over time is what we call frequency. There are several letters for frequency. And we can see that frequency and period are inversely proportional. Now, what else we know? Well, it doesn't go away further than this particular distance. This distance has a name, amplitude. So here, x, maximum x, is equal to amplitude, and the minimum on the left is equal to negative amplitude. We could sketch a graph for this experiment. Again, in this experiment, the ball was released from rest or the cart, but in this picture, it was released from a position to the left from equilibrium. So it starts from a negative value, and then it goes to equilibrium, goes through equilibrium to positive amplitude, goes back to equilibrium, goes back to initial position. Then we can sketch the graph, and it will look like this. This is the graph for one period. Well, due to certain reasons, we also use omega, which here represents the angular frequency. The angular frequency, by definition, is the number of oscillations in 2 pi seconds. That's it, not in 1 second. Frequency is the number of oscillations in 1 second. Well, so there is a slide with all this, and now we have to talk about forces. I'm going to use this example again, this simple example, because in this simple example, gravity and normal cancel each other out. They do not matter. There's only one force that matters, the elastic force from this spring. And well, right here, right now, in my example, the x coordinate is negative, but the force pushes to the right, so the x component of the force is positive. And as we know, the x component is related to the change in the length of the spring by this, or if the equilibrium x is set to 0, our law is even simpler. But this is the Hooke's law. What does Newton's second law says? Well, it says mass times acceleration equals net force. But in this case, there's only one component of acceleration and only one force. So if we combine these two laws together, we get a pretty simple equation. Usually people solve it for the acceleration. And this ratio, spring constant over mass, is always positive. Always. Mass is never negative, constant is positive constant. So due to different reasons, people call it omega squared. This is a standard expression for dynamic equation for the motion, simple harmonic motion. The acceleration is proportional to the location with the minus. All systems, all of them, all systems that have a restoring force can be described by this equation. That means if we know how to solve this equation, we know how to describe any system. Well, and what do we do now? Well, now we need to solve this equation. How do we do this? Well, we know that acceleration is velocity over time, changing the velocity over time. We know that velocity is changing the position over time. So I could use this in here, and acceleration would have been what? It would be change of the change over time. So the equation looks actually kind of complicated. Now what we have is one equation with only one unknown, x. This is actually a function of time, and we have to solve it for it. This is, of course, too complicated. Newton solved it, Hooke solved it, but Newton invented calculus for that, and we don't use calculus. So what do? We have to use a previous knowledge. Do we know any other motion that also has a period that also repeats itself? I forget this. So someone should call me and tell me, do we know another kind of a motion that also has a period? And this is also a test that we've got back and forth communication. You can hear me, you can see the numbers. So please call me on this number. Yes?
circular motion? Like,
You're absolutely correct, exactly right. So you should use a question, in your statement. You should be affirmative. It's a circular motion.
okay.
That's what we know. We've learned about it a lot. Thank you. So,
Thank you.
thank you. Now, I'm gonna again switch to the camera. And for that, I have to stop sharing this screen. And I need to... Sometimes I wish that this class would never had any Russian-speaking students. That would let me sometimes to express my feelings without being understood. All right. So this is a periodic motion which we studied, but we know another example of a periodic motion, circular. So nothing tells me I can't match the period of this motion with the period of this motion. I can just manage the length of the string, and that's it. So what can I do? Well, I can, instead of using a string, I can use my hand. If I move them at the same time, well, for now, it's not rotational motion yet, but now it is. And for this motion, which we know everything about, the motion is two-dimensional. There is X component and Y component. But the X component, the shadow of this ball, moves exactly like this card is moving. That means to describe the motion of this card, all we need to do is to describe the motion of this horizontal shadow of the X coordinate of this ball. That's it. And we're done. We will learn everything. And what do we know about rotational motion? One word answer is everything. Here we need to look at, again, the motion of this point. This point, the shadow of the ball, the X coordinate of the ball, travels horizontally back and forth exactly like this ball. So, next question. For this situation, how do you relate? This is the angular displacement. The ball actually travels with a constant speed or constant angular velocity. So how do we relate these variables, theta and omega? This is a review. And this review comes from the material before the exam, number 2, right? So, what do you say? I'm gonna check on a website. And I'm gonna send an email to IT. Maybe someone can remotely mute the speakers. All right, and on a web assign, what do we have on a web assign? This is the question number 5. We actually have 50-50 distribution between 2 and 3. The keyword is constant. So alpha is equal to 0. Technically, you could have used this equation, but because this term is 0, the right answer is this. So all we have to do now is to combine what? Well, trigonometry. In this triangle, x, theta, and radius are related. X is equal to r times cosine theta, but also theta is equal to some initial value, which usually could be set to 0. So if we combine these equations, we get motion equation, a motion equation for the simple harmonic motion done. We don't have to solve that complicated equation. We just use our previous knowledge. And there is slight difference between two motions. First of all, the language. If it's a ball on a string, of course we call it radius. But for a simple harmonic motion, this represents the maximum displacement from the equilibrium. The maximum displacement from the equilibrium has a name, the amplitude. Plus, normally we write first a term with time and then that constant, which doesn't matter. And for rotational motion, omega represents angular velocity. Now we call it angular frequency. And of course, we can also add all those relationships we used before for angular frequency now and regular frequency, the period, they all remain the same. And sometimes we may need to figure out how to write that equation if the origin was not set at the equilibrium. Why? I don't know why. Someone just wants to mess with us, but it doesn't matter. We can do everything. It just now, as we can see, this part is equal to r times cosine theta. But this part is equal to this x is also equal to well, what do I do? What do I do? If this part is equal to this part has no name, but it equals to this difference, x minus the, so x minus the x coordinate of the equilibrium. That's what it is. So we can rewrite this equation by just moving. This is the x coordinate of the equilibrium. Moving this term on the right-hand side of this equation. And this is our equation now. And again, we replace a letter R with a letter A. It represents amplitude, maximum displacement from equilibrium. And this is how the argument of cosine changes. But now this constant shifts the x coordinate. That is why usually we set it to 0. This is the general motion equation for simple harmonic motion. Now, please take a calculator, calculate 3 numbers, and if you notice something interesting, please call me. Please take a calculator, switch it to degrees, don't forget, because sometimes students forget to switch the calculator from radians to degrees and get wrong numbers. So don't forget to switch it to degrees and calculate it 3 times for cosine of 35, then negative 1 times cosine of 35 plus 180, and then sine of 35 plus 90, and then please call me. This is why having a calculator in close proximity is handy. Yes?
I just calculated all the values and they're all the same number.
Really? You sure?
Um,
Well, that is correct. Thank you. Absolutely right. That's exactly the point. They look differently, but they're all the same. What does it mean for us? It means that it doesn't have to be always a cosine. It could be negative cosine, sine, negative sine. All these functions are actually interchangeable. So we derived our equation for a cosine, but it could have been sine, could have been positive, could have been negative. So it does not matter. As long as we see something like this, it means this is the motion equation for the simple harmonic motion. And the general structure of any equation that describes a simple harmonic motion has a number, a coefficient, positive or negative, then a sine or a cosine, then an argument that may have 2 parts. One part has a time, times a certain number, and then just a number, and then plus a number. These terms, we will talk about them, they have slightly different meaning, but it doesn't matter what kind of equation you see. If it has this structure, that's an equation for a simple harmonic motion. Question: how many equations from this list do not describe simple harmonic motion? I'm not asking you which equations, yet not that. I'm asking you how many. So your answer should be from 0 to 7. If all these equations describe simple harmonic motion, your answer is 0. If none of these equations, your answer is 7. And if some of these equations describe and some not, well, your answer is some number. So please check all the equations and enter the number of equations that do not belong to this lecture, do not belong to simple harmonic motion. So far, I see only 8 responses. And again, the general structure of any equation for a simple harmonic motion is this: a number, a function, number times time plus a function, a number. So if you see an equation that violates that structure, that equation does not belong to this topic. That equation does not describe simple harmonic motion, and you need to count how many such equations you see on the screen, 1 or 2 or 3 or 4, and enter that number. So I'm checking how many students entered the answer by now. And now we've got a winning answer, which is number 2. Well, coefficient, cosine, and argument works. Why? Well, because t times 5 equals 5 times t, right? Next one, negative coefficient, negative, doesn't matter, still works. Next one, wrong. Why? It doesn't have a function, no cosine or sine. Next one, the coefficient works. Next one, the coefficient, the function works. Oh, stop. No. This is a tangent. We need cosine or sine. So wrong. Well, okay, we can rearrange the numbers, right? It should not affect the mathematics, so check. So we've got only 2 equations that do not describe simple harmonic motion. 2. Well, again, in general, there is this term that describes the shift of the origin from equilibrium. Why would people do that? But most of the time, we're going to use this specific situation when the origin is at the equilibrium. And this is the summary for that specific case for a simple harmonic motion over an object attached to a horizontal spring. But we'll learn soon, it describes everything. And this is the slide which tells us how to choose, how to change the equations if the origin is not at the equilibrium. I'm going to talk about extra variables on this slide right now. So the graph. The general expression for a motion equation for simple harmonic motion looks like this. Could have been cosine, could have been sine, as we know, never tangent or cotangent, cosecant or cosecant. And if we want to sketch the graph of this function, we should start from a pure cosine. Nothing else. No coefficients, a pure cosine. We need to know how to sketch this graph. Technically, this is math, not physics, but let's review it. So cosine of 0 is 1. So it begins from 1. Cosine of 90 degrees, but 90 degrees is pi over 2 radians, is 0. And it goes like this. It's not a straight line. It's not a circle. It's not a hyperbola. It's not a parabola. It's a cosine. And it doesn't stop there, of course. We can finish one period. It goes like this, then back to this, and then back to this. This is one period. So here we've got pi radians, or 180 degrees. this is 3/2, and this is 2 pi, radians of 360 degrees. Well, we can use radians or mean seconds. In this case, doesn't matter. This is a pure graph, pure cosine. Now, how can we change it? Well, what does the amplitude do? The amplitude shrinks or stretches the graph. The graph, well, if the amplitude is greater than 1, so this is 1, it starts from number 1 and it goes up to -1. But with the amplitude, it starts from the amplitude and it goes down to the negative amplitude. But it has the same period. So, looks like this. Oops. 1 period. All right. What does omega do? So the graph is stretched already, but the omega changes these values. Omega changes the period. So it might shrink or extend the graph horizontally along the time axis. So if we have a shorter period, it reaches the equilibrium faster, higher frequency. This is the situation for 1 period for an angular frequency greater than 1. This is a new period. What else can happen? Well, what does this variable do? It shifts the time. I can rewrite this equation slightly differently. There's what's going to be omega plus, what do I want to do? I want to have time separately. So omega t times omega over omega times omega over omega cosine 1 omega here, and this is going to be t plus this constant over omega. That's it. So we're shifting when the timer starts measuring time, basically. That's it. That makes the graph move left or right. And it still begins somewhere. Let's say the graph moved to the left, if this is positive, if theta is positive. In that case, it will look, again, the shape will look similar, like this, like this, like this, like this, but it is shifted. The whole graph is shifted to the left. And finally, if we adding and adding a constant to the whole graph, that shifts the whole graph up or down. Because the equilibrium is not at 0 anymore. So if this is positive, the whole graph is shifted from A to A plus E, and the lowest location is A minus E. So the equilibrium was shifted, and the graph will look something like this. That's what they do. However, nowadays, students don't really need to memorize all that, because nowadays you have a graphic calculator. You just enter the equation into the calculator and it plots the graph for you, and you can look at it and you see everything. And in your graph, you can measure the period from 2 peaks or from 2 troughs or from any other 2 locations with the same position and same slope. That's the period. Now, from the highest to the lowest coordinates, we have 2 amplitudes, exactly, always 2 amplitudes, 2 amplitudes. And of course, the equilibrium always in between these amplitudes. And then, if you get these numbers from the graph, if you know the period, you can calculate frequency, you can calculate angular frequency. And if you know the equilibrium and amplitude, you can write this equation. So it goes both ways. A graph from an equation or an equation from a graph. Question number 7. Is this a motion equation for simple harmonic motion? Yes, because the structure of this equation is exactly the same as the structure of general equation. You see, and they tell this is the best software for education. And by the way, it is the best, all other even worse. So this is the general equation for simple harmonic motion. This is the specific one. You need to take a look at both and make a conclusion about angular frequency. What is angular frequency? This omega. That's the angular frequency. And based on your choice, you should enter your answer into WebAssign. And I'm going to do the same. Okay, now I have to move it again. So, well, I have to match 2 equations. The specific one, which is already in front of our eyes, and the general one, sine and cosine. We've done a very similar thinking before for a different motion, for motion with constant acceleration. Now we can do this, the same type of reasoning for simple harmonic motion. This is what our match tells us. Our match tells A should be equal to -5, D should be equal to 2, C should be equal to -1, and omega should be equal to, survey says, 3 pi. That is correct. This is just a matching problem. We use our eyes and ability to match things, nothing else. Why do we need it? Because now we can calculate many things. For example, first, actually, first, let's review our knowledge about the relationship between position, velocity, acceleration, position, velocity, acceleration. Again, we keep in mind the easiest case. Let's actually do it differently. So this is the equilibrium, and in equilibrium, the spring is unstretched. what we do? We move an object to the right to equilibrium. It's important. This is 0, this is amplitude, and release from rest. Initial velocity is 0. Oh, well, this is not time, this is x. So x initial is equal to the amplitude. And of course it goes to the equilibrium, passes the equilibrium to the negative amplitude, stops there, and goes back to equilibrium, and this is one period. What's happening to velocity? It begins from 0, from rest. But how does it point? Immediately after it was released to the left, because the object must travel toward the equilibrium. That makes the component of velocity, Vx, here, negative. So negative component, negative component, negative component. When the object travels through the equilibrium, it has highest speed, but still points to the left. So maximum speed in a negative direction is reached. But then it slows down, slows down, slows down. And at the opposite side, this speed is 0 again. So, well, technically they should match. When the displacement is at the maximum, there is no motion. The speed is 0. But it keeps traveling. So eventually, on its way back, velocity becomes positive, reaches maximum again at the equilibrium, and goes back to 0. And this is one period for velocity. Well, if this is a cosine graph, this is what? A sine. And it's negative. But the graph for acceleration, oh, sorry. Now it's V, velocity. The graph for acceleration is actually even easier to obtain because we know we have derived the equation. Acceleration is proportional to position. We just have to multiply by a negative coefficient. It means we just need to, well, maybe stretch and flip the graph for position. Done. This is one period for the acceleration. And acceleration also has maximum value. Well, of course, maximum value for acceleration is equal to what? This. Maximum acceleration is reached when maximum displacement happens. Sorry, Vmax, that was X. So how do we calculate maximum speed? This is how. Why? We'll talk about it probably tomorrow. Right now it's just a fact. So now, oops, too soon. We can calculate all these variables because we know the amplitude. Well, usually we use magnitude for the amplitude. Just set it to 5, assume meters. And we know angular frequency, 3 pi radians per second. That's all we need to calculate the amplitude of maximum acceleration. We just have to multiply 3 pi squared times 5. Maximum velocity, 3 pi times 5. Angular frequency is the number of oscillations in 2 pi seconds. Regular frequency is the number of oscillations in 1 second. So we can use this relationship to calculate regular frequency. Now, as we know, people use different symbols for regular frequency, but also people use different units. This is 1 over a second. So also people write as seconds to the negative third power, but also for the frequency, there is a unit called hertz. And what is the period? Period equals 1 over frequency, or 2 pi over angular frequency. So 2 pi over 3 pi, 2/3, and that is seconds. Well, and again, in general, functions might be complicated, but we have to concentrate on 2 special cases. Special case number 1, my common example, an object was released from rest. So we had to move the card from rest and then let it go. Special case number 1. It's not a simple harmonic motion. It's not a simple harmonic motion. It's not a simple harmonic motion yet. Now, the simple harmonic motion started and is happening. Deflected from equilibrium, released from rest. In that case, the motion is described by a cosine or a negative cosine. Why? Well, if this is 0, this makes initial coordinate positive, but this makes initial coordinate negative, starts from negative something. So negative cosine should be used. And special case number 2, it is in equilibrium, and we give it a hit. Is initial velocity 0? No, this is not a simple harmonic motion. Simple harmonic motion starts right after it was touched. Simple harmonic motion. Everything breaks today. And of course, for that, for the second case, we have to use sign with a plus or a minus. What it depends on. Initial velocity might be positive, or initial velocity may be negative. Well, again, very quickly, because this is the most important case. If it starts from deflection to the right from equilibrium, it travels first to the left, stops on the left side, and starts traveling back. And the motion graph looks like this. And the equation is just a positive cosine. And for spring, 2 variables, spring constant and mass, tells us the angular frequency, and angular frequency is related to the period, and done. The graphs, again, I had them. Not very good at sketches, but good thing that's not an art class. Well, and for the acceleration, as we know, acceleration graph looks like flipped position graph. This is how we get this slide. All right, don't answer this question. We've got enough, 7. 7 is a good number. So let's just figure it out together. And what do we have here? Is it a one period? No. One period should go up to the initial location, right? But we don't need one period. If this is the whole period, how many quarters each period has? 4. That's why we call them quarters. 1 quarter, 2 quarters, 3 quarters, 4 quarters. So right here we can see 2 quarters or a half of a period are equal to 4 seconds. That means the whole period should be equal to 8 seconds. But we also see this. And this is equal to this. That's the amplitude. So the amplitude is equal to 6. And now we can calculate maximum speed, amplitude times omega, 6 times what? Well, 2 pi over a period, 6 times 2 pi over 8, maximum acceleration, amplitude omega squared. So it's rather very straightforward. Now, if we know that the mass is 100 grams, and we know the omega because it's 2 pi over 8. On the other hand, omega squared is equal to k over m. So we can calculate spring constant mass times omega squared, or 0.1 times 2 pi over 8 squared. The period, remember, was 8 seconds. And I just did it. For this special case, how does graph for velocity looks like? Well, initial velocity is 0. Now, we can look at the motion diagram. The motion relative to x-axis, the actual motion begins from rest. Okay. From equilibrium, not from rest, from equilibrium. You see the slope is not 0, so initial velocity is not 0, but it travels to the right in the region of positive numbers. That means initial velocity points to the right. So it should start from positive value. This graph for position, is actually a standard positive sine function. And velocity now looks, well, it starts from maximum, from the one we supplied by give it a kick. Then it goes to 0, it stops. And one period looks like this. So this is actually a graph for a cosine. Vmax times cosine omega t, and we know that Vmax should be equal to amplitude times angular frequency. And again, to get the graph for acceleration, just flip the graph for the position. Just flip it. A block attached to a spring moved 10 centimeters to the left, and they released from rest. Okay. We just have to imagine it. Picture. This is the x coordinate, an actual ruler on a tabletop. So this is the origin, and here we choose the equilibrium. So this is unstretched spring. Now we shift it. How? It says to the left. So this is our initial position, X initial. But also it is released from rest. So it will be moving left and right between these two values. So these are amplitudes. This is the amplitude, and this is a negative amplitude. So the graph should be a cosine, but it should start from a negative value. This is one period. And the motion equation should be so the amplitude is 10 centimeters or 0.1 of a meter, and with a minus cosine omega t. But because we know these values, K and M, we can calculate the angular frequency. The spring constant is given, and the mass is given 100. So omega is square root of 110 radians per second. The motion equation is done. And we can write the velocity equation and acceleration equation now. All right, so this is the same situation, the same block. We need to calculate something else. Find when it will be a half of the amplitude away from equilibrium. Okay. So we need to calculate the time. So we have it released from rest. It travels toward the equilibrium. This distance equals one amplitude. X initial equals negative amplitude. So of course, first time it will be a half of the amplitude here. This is x1 equals negative a half of the amplitude. And our goal is to calculate when that happens. Well, we know the equation. For any time, for any instant, it is this. So the question is when, this is the question mark, x equals negative 0.1 over 2. So negative 0.1 over 2 should be equal to negative 0.1 times cosine of 10 times the unknown time we are looking for. Well, actually, in this case, the actual amplitude does not matter. We can cancel these numbers. And we need to solve this equation. Cosine of 10 times an unknown equals 1/2. Well, now you can use a calculator. But because we need time in seconds, the calculator should be set to radians. Or you need to know that cosine of what is equal to 1/2. Cosine of 60 degrees. At 60 degrees is equal to, well, 60 equals 180 over 3, but 180 is equal to pi radians, so 60 is pi over 3. That means in order to make this work, 10 times this unknown should be equal to pi over 3 radians. For this instant should be equal to pi over 30 seconds. This is an example of a, well, kind of trigonometric equation, how to solve it. Well, in general, this is how we do it. If we have to solve an equation like this, for example, mathematically, we do it like this: inverse cosine of 1/2. And this is supposed to be in radians, because we have to use international system of units, because usually we solve for seconds. That's it. That works every time. Of course, don't answer this question, because kinetic energy is never negative. That's kinetic energy. The question is, what is happening to it? Well, again, it's a special case. For our special case, the graph of position as a function of time looks like this. That means the graph for velocity as a function of time looks like this. It's a sine, starts from rest, goes first to the left, then to the right. Done. What is kinetic energy? Kinetic energy is equal to mv squared over 2. So all we need to do is square speed and multiply by m over 2. When we square things, positive numbers remain positive, but negative numbers become negative. This will be the graph for kinetic energy as a function of time. Now you can see that it repeats itself twice in the regular period, which means the period of kinetic energy is a half of the period of the motion. Well, I'm officially done. This is over for today. Thank you very much. Let's see what's going to happen tomorrow with this room. Bye, everybody. You can leave, and I can stop. Can I? Yes, I can. Bye, everybody.